So thank you for this opportunity. So I want to say, imagine you're walking and you step on an obstacle. In that moment, you feel your foot, you feel the position of your leg, and you can counteract that event, avoiding the fall. But if you're an amputee, you don't perceive any sensation for your prosthetic device. So you're not able to react to that event, and you probably fall with high risk of damage. This is what happens if you are a lower limb amputee. My name is Giacomo Valle. Together with Greta Preatoni and Lauren Chi, I'm going to present you my leg. My leg is the first sensory feedback device for leg amputees, able to improve mobility and the cognitive integration of the prosthetic leg, providing sensory feedback non-invasively. I want to start show an example where the tactile and proprioceptive sensation are really important and connected with motor action, right? So this is a case of a rare neuropathy in which this patient suffered a completely lack of tactile proprioceptive sensation. And so easy action like walking or movements become really, really difficult to accomplish. Same problems are experienced by people with leg amputation. So they suffer high risk of falls that cost up to 40,000 euros per patient per fall, considering the hospitalization and the emergency department. Moreover, the lack of feedback is one of the causes of asymmetric walking, reduced mobility, and increased fatigue that cost up to 250,000 euros per patient, considering the sedentary lifestyle, and creates long-term medical problems such as osteoporosis, arthritis, and back pain. Finally, if you imagine to have a limb without sensation, you don't perceive this limb as part of your body, but like an external object. So you experience what is called low embodiment and low multisensory integration. And this is caused high rate of abandonment of the prosthesis, less use of the prosthesis, with the difficulty of the reintegration of the patient in the working society. Our solution is My Leg. My Leg is a device composed by a sensorized insole with pressure and position sensors that we place under the prosthetic leg, and we can read in real time during walking. Then we send the sensor to a microcontroller that translates this information in the electrical stimulation of the stump of the patient using skin surface electrode, optimally placed on the stump of the patient. In this way, the patient can have a continuous feedback during walking and is able to improve their mobility and the quality of walking. Our technology is unique because it's composed by two parts. The first one is the tactile feedback, in which we apply the stimulation on the stump of the patient accordingly to the pressure placed on the prosthetic leg, so that we acquire via the sensor placed under the prosthetic leg. And we also provide the proprioceptive feedback, stimulating the hip of the patient during walking, so the flexion and extension of the leg. So this is a remapped feedback. And interestingly, this device is an add-on for the commercial prosthesis. So we can add this device to any commercial prosthetic device. Okay? So we don't need to modify the prosthesis. The system is composed, as I said, by sensors that we place under the prosthetic leg. And at the beginning, we record and we study the placement of the electrodes and of the sensor, that we place under the foot in the main area, the most important areas, in order to detect and record the pressure and the events that are important during walking. Then we translate this information, so the artificial outputs from the sensor in the electrical stimulation of the patient, trying to create and recreate a pleasant and intuitive sensory feedback that is also processed cognitively faster by the patient in real time. Finally, we place electrode in an optimal way. So we design belt of electrode with the matrices of electrode that we can use to stimulate the skin of the patient. So the perception of the sensation is like a vibration accordingly to walking. Our device is unique because it's intuitive, it's pleasant in terms of sensation, is non-invasive, is easy to add to the prosthetic device. It is a functionally cognitive effective. So what we want to do is to improve the quality of life of patients, reducing fatigue, for example, or long-term medical problems, increase revenues for prosthesis manufacturers, decreasing the prosthesis abandonment, and then decrease also the cost for healthcare system and insurances due to false and sedentary lifestyle. Why we are the right team? Because we invented, developed, and tested MyLeg, because we have an extensive experience with people with amputation, so we know what they need, and we are highly motivated to change the quality of life of people with disability. We are part of the neuroengineering lab of Professor Stanislas Popovic at ETH, and in our team we have Greta Pretoni, PhD student, neuroscientist, that study how to integrate with the brain this device, so how the restoration of sensory feedback affect the cognitive aspects. And Lauren Chi, bioengineer, PhD student at ETH, responsible person for the electrical and the software part of this device. Looking at similar technology, at the moment, there are no sensory feedback device for prosthesis available on the market. So we identified a similar technologies in some startups or companies that mostly use invasive technology. So, or rerouting the nerve, so they need a surgery, or implanting the electrodes. In our case, we have a device that is non-invasive that play also with the optimal electrode placement. And also, as I said, is an add-on to any commercial prosthesis, so we don't need to modify the prosthesis. So our device is not a prosthesis with sensor, with electrodes, but it's something that we can add. And as I will show you next, is also applicable for other type of pathology. Why we are optimistic to be successful? Firstly, because we already tested the device using invasive approach, so we know that the sensory feedback is something that for people with the leg amputation is very useful, both cognitively, functionally, so in terms of motor actions, but also with health benefits like reducing the pain and the risk of falls. And in this case, the first prototype, we already tested the first prototype with patients in activity of daily living. So demonstrating that this device is usable also outside of the lab in also challenging situation. And the preliminary results, so we tested the system with 3 amputees, and we acquired from, we tried to analyze all the benefits of this technology, extracting the force data, the spatiotemporal parameters of gait, and also the kinematics in order to evaluate if the patient works better when the feedback is provided. And the preliminary results are that the patient perceives the prosthesis more as part of the body, that is not only more stable in walking, but also the mobility is enhanced. So that means that the patient works faster and better. And there is also a decrease in fatigue. And as you can see in these photos, we tested the system both indoor and outdoor. For the applicability, it's interesting to see that since our system is non-invasive and modular, we can apply the stimulation and the electrodes not only on the stump in a patient with leg amputation, but also with people that are, for example, people with sensory loss, like diabetic patients, stimulating above the lesion, above the nerve degeneration, or neuropathy, if you think about differentiation, or finally nerve injury, stimulating above the lesion. Proximally. Finally, I want to show you and say that MyLeg will be tested in Cybertron 2020 in the Power Prosthetic Race. Cybertron is this global competition for people with disabilities, trying to evaluate both research, prototype, and product of companies in activity of daily living in order to demonstrate the efficacy of this technology with patients. And the device will be tested by the NeuroLegs team. I want to thank you for the attention and for this opportunity. And I open now for the question. I want to thank also all the patients and the participants.
Вашему вниманию представляется проект «Разработка комплекса».
I would like to present you our project, rehabilitation system using VR-assisted technologies. You know that every year 54,000 people suffer a stroke and only 20% of them end up in rehabilitation centers. Those who do, still only a small percentage of these people can go back to work and life. Usually, when it comes to Russia, rehabilitation centers are large cities, so sometimes patients do not have access to such centers. Therefore, we need to create instruments and rehabilitation methodologies that would be available to all patients, regardless how far they live. So we gathered the statistics from the Russia's Far Eastern Federal University located in Vladivostok, so we can look at different patients and the type of traumas that the patients contacted federal centers about. So we see the majority of patients turn to rehabilitation after a stroke. We see that the number of requests from patients has been growing year after year. You see the existing rehabilitation technologies will have a comparative table or a benchmark analysis a bit later. There are a lot of patients with a lot of deficits. Sometimes we cannot transport these patients. A lot of facilities used in rehabilitation are expensive, and we need a technology that could be used for patients with different disorders. What have we managed to achieve so far? We developed a sensor prototype, we developed exercises and rehabilitation tests in virtual reality, we developed the doctor's profile and the patient's profile with a virtual model. You see an example of the tests that we have developed. All of these tests are done in virtual reality. These are motor exercises, cognitive exercises, object search exercises, and so on. You see the patient's profile. We also have doctor's profile so that both doctors and patients can monitor their success. We have also developed a motion sensor analog. As you can see, it's quite simple, but it already connects to our software. So you see the similar sensors on the right and on the left, but so they are quite heavy and uncomfortable for the patients. Here you see benchmark analysis between what's available on the market and the rehabilitation system that we have developed. What's good about our system is that we have timely reaction to test results. Let's say a doctor is in the office and she can monitor how the patient is doing exercises, so she can give the patient voice commands or correct the patient if they're doing exercises incorrectly. The second group of test subjects were using our device, and the first group of patients, the control group, they were using standard rehabilitation techniques. We see the improvement in gait parameters was at 15%. So we looked at the market, we analyzed the market for software and medical use hardware. And we think our development can be used in public hospitals, private hospitals, and we would like to market our devices to individual consumers in the future. This is our financial model. We wanted to take a bank loan of 720,000 rubles, and we wanted to reach the point of profitability by the end of the second year. This is the innovative component of our development. We also worked with the medical center of our university to develop a rehabilitation course, and so the duration of this potential course was set at 7 days. I wrote 2 articles which have since been published in academic journals. There are 3 people on our team, 2 programmers and a rehabilitation physician. This slide lists our achievements. We kicked off the project in November 2017 when we started looking into this possibility. We really liked that we can use VR to restore normal functions to our patients after traumas, after loss of some of their cognitive functions and so on and so forth. What are our plans? Well, we have submitted a patent application. We are patenting our software code and our motion tracking sensor. So we would like to further test our system, maybe see it used in a private clinic. And on this slide, you see our future plans. Thank you very much for your attention.
My name is Dinara Kagirova. Let me present to you the project of ophthalmology simulator in virtual reality from NoVR, and we are at Skolkovo resident. With me, I have the eye doctor Mikhail Katz. To understand why we launched this project, let me draw your attention to one number, which is quite important, because half of all doctor errors are made due to poor qualification of the specialists. One of the key problems of ophthalmology education is inability to study your disease using real people. Medical students cannot really work with real patients. They're overloaded with too much theory. When they graduate, they are not ready to see real patients. Unexperienced specialists make mistakes that are damaging the health of their patients and reduce the quality of medical services here in Russia. We are, as video games developers, together with ophthalmologists, we introduced to you this new tool, a VR simulator with a virtual assistant and a mentor. We have this 3D model. We reproduce anatomical portions of the eye, and they are also visualized in real time. And this allows the medical students to see in detail any eye pathology, and the existing doctors can improve their qualification. Now we will see how our project looks like. We have a scenario that looks like an eye doctor office, and then we move on to another room where you have the slit lamp, the main tool of the eye physician. And today, the user of our application may start training their skills, practicing their skills using our simulator. Software, hardware part has movements, sensor movements using Oculus virtual reality helmet. We use high-resolution models created together with ZBrush and Blender 3D to have physically correct materials and structures. We used substance designers, and to develop the entire interactive module of the simulator, combining all digital content, we used the Unreal Engine and the software was coded using blueprints. And we want to add the AI module because the implementation of those algorithms will allow us to analyze behavioral features of our user. Based on that, we'll be putting together reports for our client so that they could pay attention to a certain part that doesn't work well yet. As we analyzed it, our competitor is a specialized wet lab course. In that course, students get some theory and then they practice using a physical simulator that allows future surgeons to train their motor skills. But the full set of one workstation costs about 16 million, and one needs from 2 to 4 units like that, which is of course too much for our universities. Of course, we cannot offer the practicing of motor skills yet, but at least we have cutting-edge computer graphics and full immersion approach. There's also VR Magic with Easy IC project that's from Germany. They combine virtual reality with a physical simulator, and one station costs 25 million. And if you want to use a slit lamp to practice, you pay 10 million on top of that. And also, as a user, you have a limited amount of updates that you can get. As we interacted with specialists from all levels of medicine, has shown that there's a serious demand for our project at each level. And first of all, we focused on the hospitals and on the doctors. Of course, in the future, we want to offer our technology to the standard of training the future eye physicians. Our project is quite prominent because in 2019, the virtual reality market in medicine had shown high growth, especially during the pandemic, when it grew by 20%. In half a year of our work, we invested significant amounts into that project, into studying the market and client needs and negotiations with different partners using a variety of means to implement our project. Today, we have the eye in VR, and to get to the market, we need the AI module, something that we're working on right now, and to test it with medical universities to be able to validate the technologies and prove its efficiency. For that, optimistically, we need about 10 months. We have technical experts from different fields, which will allow us to efficiently implement our project and make it part of the market. Thank you for your attention. In the screen, you see the contacts of our research supervisor. If you have any offers, take a screenshot of this and write to us. Thank you for your attention.
Yeah, I was intending on having
one other person assist me in presenting, but with the time difference, it's a little bit brutal on a Saturday morning. So it looks like it's just me. So yeah, I'm representing Rembrandt, which is a pun on the Dutch painter Rembrandt. We're from the University of Alberta, situated in Edmonton, Alberta, Canada. And so we're the student group Alberta Tech as a chapter of NeurotechX. And so this is our team, all current students at the time at the University of Alberta, undergraduates. And so this is just a flow chart I'll be referring to throughout the presentation. And we'll just be going through as per the red outlined boxes. So the first one I'm going to be touching on is the main menu. So the overall focus of this project was to provide something in an innovative way that can be accessible to non-experts. And here we allow users to associate bandwidth magnitudes with base art features, just in a conditional dropdown. We chose to use a PyQt5 because when we can export it and have users install without having to touch the code. And then we implemented the use of a 16-channel OpenBCI. So that's their Cyton-Daisy model. And then if the user's currently unable to use that, we are then simulate a comparable data stream using LSL. So also on the main screen, we allow the users to run through a baseline, which trains a CNN for higher level art features, which we'll get to, and then actually start the main program. So from the main screen, as you saw, one of the options was a baseline. And so then that would be presenting the stimulus, which you'll see in the next slide. So we would, in our baseline, mimic a classic academic cognitive neuroscience task with triggers embedded with the onset of the stimulus. And then we would use post hoc averaging across stimulus categories. And so that stimulus would be either within the category of negative, neutral, or positive words. And so these are just some examples. The trials were all randomized and started on a blank screen. Everything was run using PyQt5. From there, the output of the baseline was a singular CSV. And then in the next slide, show you how we trained. So we use the ending of the baseline task to initialize the creation of a CNN, convolutional neural network, to classify emotional states. And so this is what my partner presenting would have focused on, but we had every 1 second, the previous 2 second epochs of EEG data. So with the OpenBCI Cyton-Daisy, that's 500 individual time points at each 16 channels. And then these are just the individual stages of our neural net. So our output was a weighted classification based on the probability of each state. And then that was passed to the next element, the art screen. And so initially we used Google Colabs to just do
Изначально поиспользовали
but that was a bit tedious and involved quite a bit of know-how. So we attempted to streamline it using Google Cloud Compute, so everything can be done solely within that user-friendly program. Then from the art screen, this being after the baseline has been run, the CNN trained. The art screen right now, it's very much an MVP or minimal viable product. So you can just associate the base features in the EEG as per bandwidth strengths with just very rudimentary art features. And we just have this series of pseudo-randomly generated donuts, which we then project the associated base brain features onto. And so we update that every second according to the classification of the past 2 seconds, according to the CNN. And then in order to maintain user engagement, we update 9 times about some small variants from the previous updates, brain-derived values. And then these base features utilize a moving baseline and buffer, and that would detect relative changes in brain activity across bandwidths throughout the session. And then actually classifying the emotional states and then drawing what those represent. Just going to go into a bit of the nitty-gritties here. We started with that live OpenBCI channel, and then we output that to a program as a LSL stream. And so these are individual data streams I'm going through on the right, which represent each portion here. So then the running stream to a circular buffer, and then we would do that basic breakdown of amplitude across bandwidths. And then we would have a classifier process, and so also running in parallel during the live art generation. We would implement the algorithm we trained and have a classification of emotional features. And then we would use the output of both emotional features and those base features into image generation. And so the CNN, that would be implemented in a way that it draws some stylistic art feature as opposed to those core elements. So that would look like warping the whole screen in some fashion.
Then I'm sorry, you have a half minute left. Okay, this is the last one.
So we will be talking about the project enhancing electroencephalography signal spatial resolution using deep learning. Me and my colleague are from RWTH Aachen, Germany, and Technical University Berlin, and we're doing our PhD thesis right now. Okay, so let's start with a small introduction about EEG and MEG. Both EEG and MEG are functional neuroimaging techniques to measure brain electrical signal. And the main difference between them is that EEG, electroencephalography, is measured by putting electrodes on the skull, while MEG is further from the skull. But both of them are characterized by good temporal resolution, with MEG and EEG having the superior temporal resolution as compared to other methods of testing of neuroimaging. The problem with both MEG and EEG, more to MEG, is that spatial resolution is very bad compared to fMRI. Now, this is not totally correct for MEG. EEG, for example, measures electrical signal, and this electrical signal is subject to signal dispersion because of the CSF and the skull, so the physical barriers. But the magnetic signal measured by the magnetoencephalography does not. And this is the cause of the spatial smearing that occurs in cases with EEG signal. This doesn't happen, of course, with MEG signal.
Sorry for interrupting you. But
Yeah.
if you share slides if you want to share slides with us, please share them, because we can't see it now.
Oh, I'm sharing my screen, am I not?
No, unfortunately, no.
No, please push the button on the bottom of your screen. And if you have any sound inside the presentation, please also. Yeah, now we can see it. Sorry, so I just detected that you forgot. Don't mind.
This is where I was talking about MEG and EEG, and now I reached the goal. So that not to lose time, let's continue. The interesting part coming, so don't worry. So the goal is to improve MEG EEG signal to become equivalent to MEG in terms of spatial resolution. So on the left, you see normal EEG signal, but we want to project that on the brain so that it becomes more spatially detectable. Okay, and now Musa, my colleague, will continue the presentation. Musa, can you do that, please?
Yeah, can you hear me?
Yeah, sure.
Yeah, we hear you.
Okay, good. So basically, I'm going to take over the presentation from now. Then my colleague will continue later. So for the data, we used a publicly available data set from OpenNeuro. It had a multi-subject, multimodal face processing. So basically, in this data set, each subject had a recording of EEG, MEG, and functional MRI. And for the training, we used only 6 subjects, 1 session for each subject, and we tested on a left-out subject. We tried doing pre-processing, but we didn't get any good results, so we decided to go without any pre-processing. So why did we use deep learning? Basically because deep learning currently achieves the state of the art in super resolution and MRI imaging. And it also have the ability to capture subject-to-subject variability, which is a big problem in EEG and BCI in general, as all of you know. Abed, could you go to the next slide, please? Okay. So we wanted first to search for the good architecture of our model. So basically, we decided to go with 4 architectures to try them and to compare between them. So the first architecture consisted of a densely connected convolutional networks block plus 6 heads of attention for 3 heads of attention for encoder and 3 heads of attention for as a decoder. And the second architecture, the second architecture was almost as the same architecture, but we also included another densely connected convolutional network in the decoder. And we also wanted to compare the effect of attention heads on learning in general. So we excluded all of them in the third architecture, and we only used 4 blocks of densely connected convolutional networks. And the final architecture, which is the 4th one, we wanted to try if we changed the input of the EEG instead of 1-dimensional into 2-dimensional, where the spatial information is encoded in the matrix-like formation. Could you go to the next slide? We used, in general, the activation function was the exponential linear unit. In the attention, we used the soft self-attention, which is defined by the softmax of the query multiplied by the transpose of the keys and divided by the dimension of the keys, so for normalization, and multiplied with the values. We got the keys and the values and the queries by doing convolutions on the channels themselves. And of course, the densely connected neural networks were as presented in the paper that presented that. Could you go next to the next slide, please? And for our validation methods from literature, we used, as the literature said, in other super resolution imaging, mean squared error. And we also wanted to kind of know that we did something correct, not only just rely on the loss function. We also wanted to get a feeling of if it actually gave us good results or not. So we wanted also to do a visual comparison of the sources of the ground MEG and the predicted MEG. Could you go? Okay. So in the result section, basically in here I'm showing the the mean squared error of the training and only the validation. So for the training, we can notice here that the first architecture and the last architecture got the best training, and this is why we decided to evaluate them on the left out subject. So, and we can see clearly from here that when we change the EEG into a 2D dimensions, we can actually achieve a much better loss than just using it as a one-dimensional. And Abed, would you like to continue from here?
Yeah, sure. So I will take over. To further validate the results, we did source localization, in which we collected the EEG data, the resulting EEG data from our model, and we averaged the epochs or the events of phase stimulation. So when the subject sees a phase, this is recorded as an event, and we average all of these events and then project them on the brain. And we compare this to what is expected in the original data compared to the output data that we produced from our model. And for example, on the right, you can see the expected results. So now comes the stimulus, and areas of the insula are lightened up, which is expected. On the other hand, our model did not show this. So on averaging the epochs, it did not show what we expected it to show, which is the signal in the insula. And this is why we say that our model is needs further improvement, as Musa mentioned. However, this has many implications when it's done. For example, in clinical aspect, we can say that better visualization gives doctors accurate detection of aberrant signals, such as what happens in patients with epilepsy. In research, better localization of neural responses can help enhance the accuracy of research and give better presentation of what they expected the subject to present, or the expected signal to be on the brain. So yeah, better spatial resolution should help both of these realms. We can also say that improving this
I'm sorry for interrupting. Half a minute, please. Okay.
Sure. So it should give us a tool to help clinicians and researchers to visualize the normal EEG into projected in the brain with better resolution. The problem with reliability is that the project did not perform as we expected, so it's yet far from the ground truth, and we will do data pre-processing and cleaning and retrain other models to improve the model. And thank you for your listening, and any questions are welcome.
My name is Alexander Sebastianov, and today I'm going to introduce to you our project of developing a digital twin of developing nano alloys using artificial neural networks. Cutting process is really inefficient in heavy machine building, and often a process expert uses outdated data from paper textbooks or some data from their own experience, and that's why cutting process is suboptimal, and that's why you lose the efficiency in production. At the same time, there's this concept, Industry 4.0, where you implement modern information and digital technologies into production. And there's this concept of a digital twin. It's a mathematical model or a set of models that fully describe the process of processing and in real time exchange information with its real physical twin running the tasks of diagnostics, optimization, and controlling the processing. System. We use a set of neural networks to control the cutting process with particular grades of steel. Here is how our system works. We get signals from the machine, and sometimes we don't know how deeply we need to cut. It can vary due to wear and tear of the instrument, the uneven surface of the blank. To find out the current depths, we use a special neural network, which based on the signal of the main drive, calculates the current depths of cutting. Then we use the updated data for other neural networks that give us the quality of the surface that we're going to get when we work on the surface of the part. And here we have a scientific publication on this topic. We're actively involved in the research. On top of cutting, we also look at milling of titanium based alloys developed by our colleagues. And the model that we are training is able to improve the efficiency of milling of these alloys. And the advantages here are that it improves the precision of processing, reduce the number of rejects, and also improve the lifetime or service life of tooling. We need to increase the resistance of our instruments and tools using this technology. We have experience of cooperating with external partners. With titanium, for titanium, we cooperate with Tolyatti State University and some partners from the Aviation University. We want to develop the digital twin of making blanks for medical implants from this particular special high-strength alloy. Also, we have some of the partners as we work with steel, some of the Tolyatti, the companies that are involved that make high-strength parts from this high-grade steel, and we improve the process of hard milling by developing digital twins that are going to control the cutting process. This is our team, our scientific supervisor and the developer of the system. I am responsible for scientific research and development, and also we have some of our university students who are involved in studying the cutting processes, and they present this project at different contests. This year we got a significant financial support. We won this special contest in the Volga region. We get the support from our own university in Tolyatti, and altogether we attracted or raised 500,000 rubles, and we will improve the functions of our digital twin, increase its abilities and functions. This is the end of my presentation. I'm ready to take your questions. Okay, we're glad to be here. We are working on this question. Can a broad smile solve the world problems? We can say yes. And we're going to introduce to you the BCI, which completely changes the experience of a musician. We have actually a video for you to present our project. If there are any problems with the connections, then let us know.
Так, пока ничего не происходит, или это так и должно быть?
Nothing is going on at the moment.
Очень тихо слышно, да, коллеги.
Расшарьте, пожалуйста, остановите демонстрацию экрана, начните ее заново и поставьте слева внизу галочку «Совместное использование звука компьютера».
Музыканты с трепетом относятся к звучанию инструмента, потому что оно определяет настроение исполняемой композиции.
К сожалению, сегодня интерфейс для управления звучанием — это либо педали,
либо ползунки. И это безумно неудобно. Но это не худшая новость.
Сегодня проработать звучание инструмента — это в некотором смысле исследование, полное экспериментов.
Но в конечном счете инструмент должен звучать в соответствии с нашими переживаниями. Почему бы ему не отзеркаливать эмоции музыканта?
Это было бы таким естественным и органичным решением, подумали мы.
И так родился наш проект.
Face Music Control. Так мы назвали эту технологию. Она позволяет управлять звучанием музыкального инструмента с помощью эмоций пользователя.
Программа считывает изображение с камеры компьютера, затем детектирует лицо. Далее она посылает часть изображения, содержащую лицо, нейронной сети, которая выдает массив с вероятностями 7 эмоций: злость, отвращение, страх, счастье, грусть, удивление и нейтральное состояние. Значения из массива приводятся к 7 типам Control Change MIDI событий, которые передаются в секвенсор, то есть программу для звукозаписи и игры на музыкальных инструментах, с помощью виртуального MIDI-контроллера. В итоге наша программа позволяет привязывать конкретные параметры звучания в секвенсоре к эмоциям.
Для этого необходимо перейти в режим настройки. Нажмем на значок шестеренки. Чтобы привязать эмоцию к параметрам звучания инструмента, перейдем в секвенсоре в режим MIDI Mapping. Кликнем на эмодзи и на соответствующий параметр. Отлично! Теперь мы можем транслировать свои эмоции инструменту, тем самым менять его звучание. Можно заметить, что тембр инструмента не фиксируется в каком-то...
Your musical tone is not recorded anywhere, but it changes dynamically, reflecting the emotions of the performer. It changes the musician's experience. The current solutions mean that there's discrete switch from one timbre to another. And this solution may be used for sound recording and for live concerts, especially during the impromptu pieces. Your improvisation piece is when you're trying to communicate the feelings and emotions that you have at the moment. And the tonality of your instrument may be even more important than when you perform a rehearsed piece. But musicians often don't have time for that. Thanks to our software, they won't have to think about changing dozens of sliders and pedals. The musicians will be able to focus on music alone and communicate their musical ideas with greater ease.
So the personality traits and their relation to genetic specificities of the dopaminergic system. Hello. Okay. Hello. As you know, dopamine is a neuromediator that plays an important part in the brain reward mechanism because it generates the feeling of pleasure. Therefore, dopamine plays an important part in cognitive function. So dopaminergic switch is required for a human being to switch their focus from one type of activity to another. Dopamine allows us to learn from our mistakes, and if there is a dopamine deficit, then we cannot learn so successfully. We use GWAS or polygenomic search for association. So we can use GWAS to find the same genetic feature. And for this study, we use genomes of different participants of the study. So we're looking for SNPs from different participants, and we looked at different behavioral phenotypes. We looked at intellect, and by intellect we mean cognitive abilities. So we took the genes that, according to different scientists, were associated with intellect. And all of these genes also participate in dopaminergic system. For instance, PTEX3 protein participates in the formation of the ocular lens. It also participates in the signal differentiation of dopamine neurons, and it plays a part in the formation of the substantia nigra. So we were able to look at very strong SNPs or polymorphisms that we see in some people, but we don't see in other people. So we wanted to look at strong SNPs and to see whether they can be encountered in a different dopaminergic group. So we decided to come up with an algorithm that would be able to sort through the SNP table. So the strong SNPs are those with a p-value of greater than 0.06. So we were looking for the single nucleotide polymorphisms in genome 1. If we didn't find it, then we were looking for a weaker SNP and also looked for it in genome 1. Then we repeated the sequence, so we were able to determine which weak single nucleotide polymorphisms correspond to all weak SNPs. As you can see here, and this is a visualization of our algorithm. This is the textual representation of the algorithm, and these are the genomes that we selected for processing. This is the tool that we used, and
Для чего же все это нужно? В современной науке, где существует огромное количество данных...
Why do we need to do this? Well, you know, it's very important to process data correctly, especially when we're dealing with a lot of data. So our research brought us one step closer to decode the genomes and phenotypical features of human beings. So we conducted the first part of the study, and now we want to look at human genomes from open data sources. We want to process all of the SNP statistically, and then we can group them according to their biological functions. So this is our team.
Thank you, dear friends and colleagues. This was really an important conference with excellent momentum. Our huge team that did all this work to organize the contest and to tally the points all did a good job. We had people from Irkutsk, Moscow, Makhachkala, Stavropol, Saratov, Orenburg, Ufa, Kemerovo, Orel, all over Russia. And in Irkutsk is 20 minutes past midnight, and guys are waiting for the results. Let me give you the list of winners. The first prize in our integrative brain function Olympics goes to Irkutsk team. They're called Spike. They got 137.75 points. Big Brain Time gets the second place, 120.49 points. Our third place, we will have two third places. There's only a gap of 0.4 points. That's the Pere Aude of Pirogov University, and also Grasshoppers from the Sechenov University, 114 points. Okay, Neurolink gets from Dagestan gets place number 4 with 111 points, and two teams were very close of below 0.5 points. We decided to award 2 fifth places to the Samara University and Pattern of Victory team. They had issues with connection, but they overcame them all and did a good job of doing the tasks. Pattern Victory, 106 points. These 5 places, 7 teams, 2 third places, 2 fifth places, and congratulations to all professors there on training such great teams. They will get awards that we are going to mail them.
Well, we also have an award from our viewers. So 3 teams have won in the video category. So they have the Spectator's Choice Awards, Eureka, Spike, and Pattern Победы from Stavropol. So their videos have won the Viewers' Choice Award. Everybody did a great job. I am happy to congratulate all of the teams on their effort and on their hard work.